Imagine we have 2 point charges, one capital Q, one lowercase q. Let's picture the electric field due to the charge capital Q. Of course, each of the 2 charges has an electric field that it creates. But I want to picture how the charge lowercase q is responding to the charge capital Q. We could do this the other way around. Instead of saying that lowercase q is sitting in capital Q's electric field, we could picture how capital Q is sitting in lowercase q's electric field. Either way, the force they exert on one another is mutual and governed by Newton's third law. So it's arbitrary which one we say creates the field and which one experiences the force. They both create a field and they both experience a mutual force. So there are several lines of equipotential that are concentric circles around charge capital Q. So this charge lowercase q is sitting at some value of electric potential. Let's make it easy to move this. Okay, so let's say that lowercase q was sitting at the high electric potential and then moved to the lower electric potential. So as you saw in the previous video, then work would be done by the electric field. Work is the integral of f dot ds. In electrostatics, the force is found by multiplying the charge times the strength of the field. This charge is just some singular value of coulombs we can take out of the integral. Work is Q times the integral of E dot ds. Now, unlike the example in the previous video lesson where we were dealing with a uniform electric field, we can't take the value of electric field out of the integral because the electric field strength gets lower and lower and lower the farther away we get from the charge capital Q, which you can see the spacing between the lines is getting greater and greater and greater. So we say that the work is equal to Q times some negative change in electric potential. Okay, so that's it. This must mean that negative change in electric potential is the integral of E dot ds. Or probably better to say that change in electric potential is equal to negative the integral of E dot ds. Now, whenever we think of change, we're always going to take some final value minus an initial value, right? So if the charge Q, lowercase q, moved from equipotential A to equipotential B, then the change would be the value of electric potential at point B minus the value of the electric potential at point A. Of course, we know that would be a negative value, right? After all, the electric potential at point B is low and the electric potential at point A was high. And again, that's all assuming that this was a positive charge, and that's the notation I want to go with. So VB minus VA is equal to negative the integral of E dot ds. Of course, this is a line integral, right? So we should have some upper and lower limits, although we don't actually have any numerical values that we gave in this case. So we can just say that we were starting at potential A and ending at B. Now, I'm not really a fan of any equations in which I have to consider a negative sign. So we can get rid of that if we say VB minus VA is equal to positive, and then we just change our limits. B to A, E dot ds, right? Well, here's the thing. It's really hard to say what electric potential is. It's kind of arbitrary. But change in V is absolute. What do I mean by this? Well, this idea always reminds me of our introduction to potential energy and example problems that involve roller coasters. Maybe a roller coaster cart starts from rest, initial V is equal to 0 here at point A, and then it rolls downhill, ends up at the top of the hill at point B, at the bottom of this dip at point C, at the top of another hill at point D. And then I ask the question, what is the gravitational potential energy at this point B? Well, that's kind of arbitrary, right? Maybe it's equal to 0. Then all I know is the gravitational potential energy at point C must be negative. At point D, it's positive, but not as great as it is at point A. In other words, if I want to make a reference level where I say gravitational potential equals 0, then everything from there has to fall into place relatively. Of course, maybe it would be more convenient to say, no. The gravitational potential energy is equal to 0 at the very lowest point, at the dip at point C. Okay, well then, the gravitational potential energy at points A, B, and D are all positive. Then again, they could all be positive and greater in magnitude if I'm picturing this roller coaster as raised up even higher above the ground. Maybe the gravitational potential energy equals 0 here. Anyway, this goes on and on. I can say that the gravitational potential energy is 0 wherever I want, so no two people will agree on values of gravitational potential energy, but they'll always agree on what the change is, right? Regardless, the change in gravitational potential energy as the roller coaster goes from point A to point B is the same regardless of whether you choose 1, 2, or 3 as your reference level for 0 gravitational potential energy. So the same concept applies to electric potential. The values of electric potential are arbitrary, but the change has to be agreed upon. So it might be convenient to just choose a reference in which we set the electric potential at point A equal to 0. Then in that case, we would get the electric potential at point B minus 0 is equal to the integral from B to A of E dot ds. Okay, so this is a important general equation that we can use, and I'll show you an example of where we might apply this. What if we had, let's say, a uniformly charged rod, and we want to know how much work is done by the electric field as some charge lowercase q moves from point A to point B. So we'll say that the rod carries a charge capital Q. Well, if we can figure out what's the electric potential at point A and what's the electric potential at point B, then the work is just equal to the charge Q that's moved times that difference in electric potential. Okay, so one thing, we probably already have an idea that we can use Gauss's law to come up with a formula to describe how the electric field varies in strength in the region surrounding this charged rod, provided we don't stray too far, so we're in the region that the electric field starts to become non-uniform, right? So in this unit of study 2.1 on electric potential, we'll often be interested maybe in questions that go a step further and even say, if the charge was released from rest at point A, how fast would it be moving when it gets to point B? All right, there's a couple ways to do this. Often if we want to find out how fast something's traveling after it's gone a certain displacement, if we can identify the initial speed and we're asked to find the final speed, and maybe we know the displacement, then as long as we also have an acceleration, we could use an equation like v squared equals v initial squared plus 2a times the displacement. Problem where we're not even interested in the time spent moving. Of course, this equation is one of these sort of kinematics equations that's only valid if a is uniform. And the only time that acceleration is uniform is if the force is uniform. And the only way an electrostatic force is uniform is if the electric field is uniform. But we know the electric field around a charged rod is non-uniform. Now in this picture it looks uniform, but remember that if an eyeball was looking here, that the electric field around the rod is actually non-uniform. It gets weaker and weaker the farther out you go. In fact, I think you know that the electric field would be proportional to 1 over r. So we can't actually use kinematics. So what's the next best choice when trying to figure out final speeds? We can use the work kinetic energy theorem. We can say work equals change in kinetic energy. So if the object's released from rest, then we can replace change in kinetic energy with 1/2 mv squared. How do we calculate work? Well, it's q times delta v. So the final speed would be equal to 2q delta v divided by m square root. And now you notice why I use this notation for v, why I always put that little hook on it when I draw it. I don't want to confuse my v for velocity with my capital V's for electric potential. Okay, so that's exactly what capital V represents. Electric potential, it's a quantity measured in joules per coulomb. Delta V is nothing more than some final electric potential minus some initial value of electric potential. There's a name for that, other than calling it change in electric potential. We call that a voltage. Okay, we don't call this voltage, we call it electric potential. But whenever we calculate a difference in two values of electric potential, then we can refer to that as a voltage, which of course is also going to be in joules per coulomb. We might want to know if this is made out of plastic, what's the electric potential, and this is solid, a solid plastic sphere. Maybe we want to know what's the electric potential right at the very center. Maybe we want to know what's the electric potential right at the surface. Maybe we'd like to know what's the electric potential at some distance r away from the center. Or even what's the electric potential somewhere way off the screen. In fact, we might say infinitely far away. We might even want to know if we change what r represents, maybe it's not the distance to a point outside of the sphere, but to a point inside. So how do we figure this out? Well, we say that the electric potential at point B is equal to the, minus the electric potential at point A is equal to the integral as we evaluate from B to A of E dot ds. Okay. It will be convenient if this was equal to 0. So we might say, let's let V equal 0 infinitely far away. So for us, A would represent a really big radius equipotential surface. Obviously, I can't draw the one that represents infinitely far away. You get the idea. So we'll say VA is at R equals infinity. And I want to know what's the electric potential. Let's try to figure it out at this point. Okay, so forget all these other ones. Okay, well, then that's at V equals question mark at R. So if I'm defining the electric potential to be 0 at a point infinitely far away, remember our conversation about the roller coaster, I can define gravitational potential energy to be 0 wherever I want. I can define electric potential to be 0 wherever I want, and I want to set it equal to 0 at a point infinitely far away. Then the electric potential at this point B that I'm trying to solve for would be equal to, well, I could say VB minus VA, but VA is 0. Okay, so then as we go from R to infinity of E dot ds. Although there's a little bit of a problem here, because the formula that describes the electric field inside a uniformly charged sphere is a totally different equation than the one that solves for the electric field at points outside. In fact, I think you know what the graph of electric field strength versus distance from the center would look like. Now, of course, if that sphere was made out of metal, it would look like this. The electric field value would be all 0 until we get up to the surface, and then from there it drops off as 1 over r squared. If it's made out of plastic, the difference is the electric field is not equal to 0 at all points, but actually increases linearly as we go from the center outward. So it's discontinuous. There's an electric field at points inside this plastic sphere, and there's electric field at points outside. This one is proportional to r to the first. This one is proportional to r to the negative 2. So I actually can't calculate this as a single integral because the E is represented by two separate functions. So I would actually have to say that the electric potential at point B, kind of silly for me to write minus 0, right? I'll get rid of that term. The electric potential at point B, I could say is equal to the integral from lowercase r to capital R, right? There's our lowercase r, of E in dot, I suppose I could change ds to dr, plus the integral from r to infinity of E out dot dr. Well, I think I'm starting to get a bit too far ahead of myself now. We'll complete this derivation in a future video lesson, but I do want to make, at the very least, a reminder of these two important distinctions about electric potential and electric potential difference. So, electric potential, like gravitational potential energy, is somewhat arbitrary. We can set it equal to 0 wherever we want. And whenever there's a change in electric potential, that's what we refer to as a voltage. And one of the most important guiding formulas we'll be applying in this unit 2.1 is this circled formula. And if it ever comes to solving for the motion or the speed of an object, know that kinematics often can't be applied, but the work kinetic energy theorem can. Okay, so there's a teaser of things to come, and thanks for watching.